So last class, we were looking at solving the infinite potential well problem. And also we started initially with solving Schrodinger's equation in a free space, completely free space. And then we solved it in a infinite potential well. Before I finished the class last time, I think there was something I forgot to do, which was to find this normalization constant, right? So that normalization constant turns out to be root 2 by a, and how you get that is you integrate the wave function from 0 to d, and you set it equal to, integrate the probability from 0 to d, and then set it equal to 1. Then you'll get this integration, right? So this a actually turns out to be root 2 by d. Okay. Yeah, it's root 2 by d. Okay. I wanted to also show you this file, and Monica can share it with you. This is available on Google also. Same derivation like how we have done, except in a different way if you want. And also, if you want to go through a slightly different way of doing it, you can check this out. It's very similar to what I have done, right? But if you wanted it a little bit of a clean derivation, I would suggest this, right? So how you get this is, if you simply ask for infinite potential well solution. So very first one, it's a University of New Mexico page, okay? This one, infinite square well, right? So solve it exactly how I have solved it only, nothing different. But if you want something nicely typed out, in case you want to work it out yourself, I would highly recommend this particular note. And so yeah, as you can see, the normalization is root of 2 by a. And he has shown the derivation also for that. Okay, right. Right. So before we proceed into that further, let us quickly revise and summarize what we have learned so far. When we looked at two things, right? So first thing we looked at is free space, Schrodinger's equation, time independent only, and then second one is infinite potential well. And it's actually also called the square well because it's a shape, it's not really square. The reason it's called square well is, this is 0 here and suddenly it goes to infinite. In some cases, you might also see this energy labeled as 0 and this is labeled as minus infinity. That's also not a problem. Remember, energy is always measured with respect to some reference, right? So we can put the reference anywhere. If we put the reference at the edge of the well, then the electron, whatever energies that the electron has, will always be negative energies, right? So what it simply means is it's negative with respect to whatever your reference is. So the reason I'm telling you this is different books and different notes, you may see different conventions. It shouldn't confuse you, right? It's just, when I say E1, E2, energy is always relative, right? So our earlier derivation, we took this as 0 energy. This is a point of 0 potential energy. So with respect to that, other energies are positive, right? So I hope this is clear to you. Depends on where I take the reference. In the future also, this will become very important. You're looking at the energy diagram for graphene or something like that. Sometimes you'll see negative energy. They'll say, okay, Fermi energy is -1 volt, electron volt or something like that. That shouldn't confuse you, right? You should have to first ask, okay, before we are even talking about energy, where is the reference level? Okay. In the case of a universe, where there's nothing, then the zero energy is, then energy has to be always positive, right? There the zero is clear as to where that zero will be placed at. In the potential well, two possibilities. You can put the zero at the top of the well, or you can put it at the bottom of the well, wherever. So I hope that is clear, right? Before we revise the solutions, what kind of equations we got for the wave functions and so on, so I guess let's first do that. So the solution for the wave function in a free space turns out to be some constant a, and if it's infinitely extended, we cannot really normalize a, right? It's almost zero only. So I'm just going to leave it at a. So because this is not normalizable, that's the reason. E to the power j e by h bar t e to the power plus or minus j kx, where k is root of 2me by mod h bar square. This e here and this e are both the same. Okay. So this immediately must tell you that the momentum and energy are somehow related, right? And they're somehow related. And let us see how they're related. Generally, this is where they draw this dispersion diagram, right? EK diagram, right? That comes from this idea. You can see that the energy of the particle is E, and its momentum, which is h bar k, they're related, right? Because both have the factor E in there, right? Let us find that relationship. So for this free electron, the energy is h bar omega, and the momentum is h bar k, which is actually equal to h bar into root 2me by h bar square, right? Or k is nothing but root of 2me by h bar square. There is a relationship between E and K. Let us plot that, right? So if we plot that, E is always on the y-axis, and K is always going to be on the x-axis. And E versus K, as you can clearly see, it is nothing but E is nothing but h bar square K squared upon 2m. So when E is 0, when K is 0, E is also 0. And if we plot this is very important, okay? This idea is very important. I want you to thoroughly understand this idea. It's going to be a parabola. This is your dispersion diagram. This kind of a diagram where I plot E versus K, it's called a dispersion diagram. And so this equation of this parabola is E is h bar square K square by 2 mass. Now we can observe some things. If the mass is very low, then for a given, so if I take two different particles and I was to plot their dispersion diagram, this is just free space dispersion diagram only, okay? And you can see that this is for a lighter particle, it's going to be for a heavier particle. So if I because we are also quantum objects, you and I, if I was to take your I can plot a dispersion diagram for you also, and it will be very, very flat, right? It will be very dull. Now, we can do this kind of diagram for light also, right? Even for a photon. And let me show you what that looks like. So the energy of a photon is h times nu, right? Or it's same as h bar times omega. And the momentum of a photon is h bar into k, and that is h bar into 2 pi by lambda, where lambda is the wavelength of that particular light. This can be written as h bar times 2 pi c by f, can be written as h bar by c 2 pi f, or can be written as h bar omega by c, right? So moment h bar k, which is a momentum, can be written as h bar omega by c, or k is nothing but omega by c, or omega is nothing but c times k. Okay, now what is energy of the photon? Energy is h bar omega. So if I was to plot the energy of a photon versus k, it would look like a straight line, right? Here. And see the difference between a massive particle and a massless particle. Massive particle dispersion diagram is always parabolic, whereas for a massless particle like a photon, it is a straight line. What is the slope of this line? Slope of this line is E is h bar c k. Slope of the line is h bar c. Okay, slope. So slope of this line is tan of the slope is h bar c. Okay. Yeah. And what you will typically find is that if I was to, on the same diagram, I can now plot it, right? If I was to plot the E bar k diagram for a photon, it would be very steep. So in other words, for the same energy, the momentum carried by a photon is very low, which is obvious, right? Because it doesn't have a mass. So a photon can have same energy as an electron. You can shoot them both give them both the same energy, but the photon will have lesser momentum. So example would be, if I was to take a ball, right, and throw it at 10 meters per second, for example. Well, that doesn't completely answer the question. Let's say both have the same kinetic energy, and I hit you with that, right? Clearly p square by 2m. So the bullet, smaller object, should have more velocity, right? So same kind of idea, but we cannot extend it so easily to photon. The photon actually has zero mass, okay, but it still carries a momentum, and which is momentum is mass times velocity, right? So if mass is zero, how can the momentum be non-zero? It can be, because it comes from relativity. So momentum is equal to mass times velocity is a classical relationship. Relativistically, photon is a relativistic particle, so you cannot use the formula for normal non-relativistic momentum formula. So in other words, photon also has a momentum, and its momentum is very low, quite low, actually, not very low, it's quite low, right? Okay, so we understand hopefully the concept of a dispersion diagram. This becomes very important because in a next situation, we go to a more complicated thing like electron in a crystal, for example. There also, the wave function will be looking more complicated than this. It will not be so simple. But there also, there will be a relationship between its energy and its crystal momentum, actually. That relationship, E versus K, is what you draw and what you know as the EK diagram, right? That is what you look at a band diagram, you can draw these kind of things. And now you get an idea why that band diagram can give you the mass, right? Because see, there also, if the whatever you plot for a crystal is looking like a parabola, you know that wherever it looks like a parabola, it must have some kind of a mass, right? So the slope of the parabola, the dispersion diagram, this is why the slope gives you the effective mass. Okay, we'll look at it more detail later on, but I hope you understand the idea for a simple particle in vacuum. Notice that these dispersion diagrams are continuous for a free particle. Not surprising because we already figured that out, right? Now, when we do the dispersion diagram for a, okay, that is what we did in the first case. I hope there's no questions about this. So we move on next. I hope this idea of dispersion diagram is clear. Very important concept, right? Once you solve Schrodinger's equation for any electron system in any potential, the biggest information you get is this dispersion diagram. Although people don't tell this to you. Very important that you understand the concept of a dispersion diagram. Great. So that's understood. Now let's go to the second case. I guess before I do that, let me clarify a few things again. This is the wave function for a free particle in vacuum, right? It is a energy eigenstate. It is also a momentum. Yes.
What is the use of this dispersion diagram?
Yeah, this dispersion diagram will tell you, for example, let us say I'm doing some electron emission process, for example. Then we have to conserve momentum, right? Then we look at these kind of diagrams. Okay, that is one use for these kind of diagrams. Plus, it tells you how the energy and momentum are changing. And for example, here, see this straight line I told you, dispersion diagram of a photon will look straight line, right? It turns out that if you do the dispersion diagram for electrons in a graphene lattice, there also you get a straight line. So, right, so these are called massless fermions. So very, very interesting concept. I'll deal with it later on. But a good idea for you is that dispersion diagram summarizes the Schrodinger's equation solution in a nice graphical way. Is that convincing to you at this point?
Yes, sir. Okay. Thank you.
Thank you. Yes. So, yeah, please.
Sir, I just have a few questions.
Yes, please.
Can I ask? Okay. Sir, the earlier classes, you said that the wave function is an infinite dimension vector. Sir, so can you just can you explain me that in which case will it be an infinite dimension vector? Like, if it's
see, I'll explain to you. Okay. I'll explain to you, right? So, see, if I have a if I have a function f of x that is defined on the real line, then if you have to specify it in the form of a table, then you need infinite numbers, right? How many numbers are there between 0 and 1?
Infinite numbers.
Infinite numbers. So if I have to specify some arbitrary function, okay, in the form of a table, right? I'll say, okay, at 0, its ka value itna hai, 0.1 pe itna hai, 1 pe itna hai. That's not enough, right? Then you'll ask me, okay, what is its value at 0.01?
Right.
So do you see where the infinite idea comes in?
Right. Okay, sir.
Yeah, it's a little abstract.
Right.
You see this, right? But it's a very beautiful idea, right? Not at all obvious. It's not at all obvious. See, this was I would say this was actually the invention of this German mathematician Hilbert. Okay, so they looked at normal vectors. I mean, can you imagine anybody coming up with this idea, right? That everybody, did you come on? Would you have come across this idea on your own? Not really, right? It's a very, very strange leap, but it is correct. Once I explain this to you this way, then you say yes, of course, that is the case, right? Okay, that is your question. Any other question you have?
Yes, sir. So, sir, in this means that even if the wave function is localized up to a certain extent,
doesn't
so
matter. Then also it's an infinite dimensional vector only. Yes, yes. That is the reason why we can, the Hilbert theory, Hilbert spaces, right? That is why quantum mechanics is always described in terms of Hilbert spaces. So even if it is localized, it is still an infinite dimensional vector.
Right, sir. Sir, and last question is that, sir, here psi is an eigen function or an eigen state. Like in some books I have read that psi, they mentioned that psi is an eigen function. So are they both same? Like,
Right. Okay. So Eigen, in my opinion, the word eigenfunction and eigenstate, I would think of them as synonymous, right? Because because see, I told you where my idea of eigen thing comes in, right? Eigen, when I say eigenstate, the immediately you should ask eigenstate of what, right? Then the answer is, when I say it is eigenstate, there is immediately your question should be of what operator, right? So it must be a solution of some particular operator, right? That is why the idea is a eigenstate. So see, if I take this particular function, it is a function, and it's a quantum state also. It's a state also. So if you are thinking in terms of mathematically, solving a differential equation, then it's an eigenfunction. But when we then go into the physics of it, then we say, yes, this is an eigenstate. Is that answer clear to you? It's a
yes,
context,
sir.
right? You can talk of a function when you're doing the mathematics of it. Then when we think of the physics, then we can say this is an eigenstate, this is a ground state, like that.
Right, sir. Right, sir. And sir,
Clear?
so the
Yes.
same goes for eigenvector also, right? Like when we are working on matrices, then we come across eigenvectors.
Yeah.
And then,
Eigenvector. See, if you say this is an eigenvector, it doesn't have any meaning. So if you say this is an eigenvector, my question is eigenvector of which matrix?
right.
You got it?
Yes, sir. Yes, sir. Thank you, sir. Thank you.
It's a property of the matrix. Similarly, here, it's a property of these operators.
Right.
Great. Thank you. Any other question, guys? Folks, sorry, don't mean to be specific. Anybody? Yeah. Any question? Great. So let's proceed, right? This is clear. This is actually very, thank you for reminding, this is a very important idea, right? In your head, you need to start thinking of these wave functions as infinite dimensional vectors. And you need to start thinking of operators as some kind of infinite dimensional matrices. Why? Because I am in this course, I am giving you a very intuitive sort of, first principles kind of explanations. But if you take an advanced quantum theory, then they only talk about, vectors, eigenvectors, Schmidt decomposition, all kinds of, jargon will come. Then you should not feel that, अरे यार, this Ravi कुछ तो कहानी बोल के भेज दिया हमको, कुछ इससे समझाया नहीं. Not really, right? I am giving you the ideas there as well. Although I'm not using a very mathematical language, the concept is there. Great. So coming back, so these functions, free space wave function solutions, these are energy eigenstates, and they are also momentum eigenstates. Okay, they're not position eigenstates. No, they're not potential energy eigenstates also. No. Well, potential doesn't even come, right? It's free space. Yeah, they're not position eigenstates. Great. Okay, so now let's go to the second problem that we encountered, which is infinite well. And what was our solution? Our solution is in this format. Psi x of t, the eigensolutions for this case was this root of 2 by d sine, let me look at the n pi x by a, I believe. Yeah, it's n pi x by a, n pi x by d, sine of x by d, where I'm going to drop this time dependence, okay, for now. I hope you permit me. I'll tell you why we'll drop the time dependence for now. So I'm going to call it size sub nx. Okay. So these are the nth eigenstates, energy eigenstates, and n can go from 1, 2, 3 all the way to infinity. And for any particular, these are energy eigenstates, and their eigenenergy is n square, h square, pi square by n square h square pi square by 2md square. md squared. Okay, so these are the energy eigenstates. Now I can ask you what is the dispersion diagram for this particular solution, right? So let's do that first. So I'll do the dispersion diagram. What is the possible value for k? H bar k, right? And remember, k can occupy value n pi by d. Okay, k will be n pi by d. So go ahead and first value is 0 will not a solution. Next solution is 1 into pi by d. This is k basically. Remember I told you plus or minus k are the same solutions. So we can do this for the other case also. And 2 pi by d, 3 pi by d. These are the possible values of k. And for each value of k, I'll have an energy, which is h bar square k square by 2m. So it is n squared, right? So this first E1 will be here, E1. Then for this particular case, it will be 4 times E1. Same for this state also, minus pi by d also. It's a similar thing. Okay, so it is like this. It's also looking parabolic in a way, but it's not a continuous curve, right? So now if your d is quite large, then these will come very close and then it will start looking like a parabola. But otherwise, they're distinct states. So this is your EK diagram for a infinite potential well. And these are the solutions. And now I'll tell you some very strange properties of this solution. If I ask you, we already proved that these are energy eigenstates, right? They're energy eigenstates for sure. Why? Because if I operate with this, I can do the kinetic energy operator on this minus h squared by 2m into delta d square by dx square. You get again, if I operate with a kinetic energy operator on this particular state, I'm going to get some scalar multiplied by phi n. What scalar? This particular scalar, right? I'll get this en multiplied e into psi n. I'll get this back. Okay. Okay. These are also basically, you have to multiply it to the time operator, right? So these are also for the total energy operator also. They're eigenstates of the total energy operator also. En times, if I convert it into a time form and then use the energy of total energy operator, so that it's a kinetic energy eigenstate. It's also energy the simple energy eigenstate also, right? But you'll be very surprised to find out that this is not a momentum eigenstate. Okay, it doesn't have any momentum. Why is that? You can see this, right? What is the moment? This will be surprising for you. What is a momentum operator? It's nothing but h bar times minus I h bar d by dx. Let's operate on this, right? 2 by a sine of n by x by a d. Let me be consistent here. D. If you go ahead with this derivation, I'm going to get I h bar root of 2 by d. Differentiation of sine is cosine n by x by d multiplied by n pi by d will come outside. And what have we done here? We have basically done p times phi n. And if it was indeed an eigenstate of the momentum operator, I should have got some scalar multiplied by phi n. But no, I get cos here, right? See, my original function was a sine, I get a cos. So this is so there is no this is not an eigenstate of the momentum operator, right? And you may be wondering, okay, what the hell is going on? Because I'm assigning a k to it. I'm assigning n pi by d to it. But you're asking, why is that, right? The answer is very nice and very tricky. The answer is that, see, we cannot differentiate between plus k and minus k, right? That is the answer. Okay. And the eigenstates of the momentum operator are either forward traveling waves or backward traveling waves. But what the solution we have here is a sum of forward and backward. In other words, we have a standing wave. We don't have a traveling wave. So standing wave, because we have standing wave is not the it's not an eigenstate of the momentum operator. Okay, so it's a very tricky question. Somebody will ask you if you're doing if you say, they'll ask you first, yes, do you know quantum mechanics? You'll say yes. Actually, we do this in our interviews occasionally. The next question I'll ask them is, okay, great, quantum mechanics, that's fantastic. Do you know solution for the infinite potential? They'll say, yeah, absolutely, man, that's very simple. Then I say, okay, great, fantastic. So what is the momentum of a ground state, for example? There is no answer. It doesn't have a momentum. It doesn't have a definite momentum. Why? Because it's not a traveling wave. And so it's not an eigenstate of the momentum operator. It has a K, okay? But it has a K, but that K is actually, I cannot differentiate between plus and minus K. That is where the uncertainty comes from, right? So anytime you catch this particular guy, electron, he could be going forward or backward, because he's just in the wall, right? He's bouncing back and forth. So anytime you catch him, you could catch him when he's going forward, or you could catch him when he's going backward. And so you cannot assign a definite momentum. Okay, I hope the idea is clear to you. Although we have a K, we have a definite value of K to it, doesn't have a momentum, doesn't have a direct momentum. Okay, and it's correct also, right? Because see, it's trapped in the well. If it has a momentum, it should have been going somewhere, right? It's not going anywhere. So if you actually find, if you ask me what is its average momentum, it should be zero, right? Should be, what is the expected value of its momentum? Should be zero, because half the times you're going to find it going forward, half the time you're going to find it going backward. Okay, so I hope this didn't want to confuse you, but just to let you know that if you understand every material I've covered till now, this somewhat abstract idea should be clear to you. Okay, if not, think about it. Okay, so these are not energy eigenstates. These are energy eigenstates. They're not momentum eigenstates. They're not position eigenstates also, because they don't have a definite position, right? So the ball, so the electron in the well cannot be anywhere. Sorry, can be anywhere within. It doesn't have a different momentum. Okay, let's look at this. Now we have looked at mathematics. Let's look at this wave function a little bit more carefully and think about it, right? So this is my infinite well. And the very first wave function is going to be of the form 2 by A. Very first eigenstate, sorry, let me use the correct word. Pi n pi x by A. So pi x by D. Okay, this function, we're going to plot it, right? So if x is 0, it's going to be 0. If x is D, then also it's going to be 0. Right? So remember, we should never plot the wave function by itself. We should always plot its square, right? So I want to square this, then plot it. And when I do that, I end up with a function that looks something like that. Okay. So from this, we can say very highest probability of finding the electron is exactly at the center of the ball. Physically, why? Because, like I said, this ball is just, it cannot be quiet. It cannot be stationary, which means it is moving. But it cannot be, so it can be moving either forward or backward. And it cannot be moving entirely forward or entirely backward. So it is, occasionally doing both, right? So imagine bouncing between wall to wall. Very high chance of you being found near the center, right? Even if you're going forward or backward, right? So that's it. Okay, I hope you are visualizing why this is happening. Yes, so has a highest probability at the center. If I look at the second wave function, that is going to do something like that. It's not negative, right? Why not negative? Because probability cannot be negative. Okay, I'm squaring it, right? I'm squaring it. So this is the second wave function. And if you do the third wave function, third eigenstate, sorry, you're going to do something like that, right? And yeah, so second, yeah. So fourth wave function will have, right? So you see what is the cool thing here? It's the zero crossing idea, right? So how many times your particular eigenstate probability crosses zero? And in fact, this is a very well-known thing, and so that we have a name for it, it's called the zero crossing theorem. Zero crossing theorem. The zero crossing theorem says that if you want to solve Schrödinger's equation in a potential well, right now we have taken this particular shape where this is going to infinity. But I could have a well that is doing something like that, right? Or some very complicated well like this. It doesn't matter. It doesn't even have to go to infinity. What the zero crossing theorem tells me is something very powerful. It says in any general well, okay, so in a very complicated well like this, your answer will not be so simple. It will not be so simple. It will be something very complicated. Doesn't matter what it is. The first eigenstate will have no zero crossings in the middle. Second eigenstate, n equal to 2 quantum number, will have exactly 1 zero crossing in the center. Third eigenstate will have 2 zero crossings in the center, and so on and so forth, right? So you give me any arbitrary potential well, okay, something very complicated like this, and ask me, go ahead and solve the Schrödinger's equation in this particular well, or I'll kill you, right? I'll say, you know what, I cannot solve it exactly because I don't have Mathematica with me, but I can tell you that the wave function looks something like this. First one would always look like that. Second one would always look like that. Third one would always look like that. I can tell you, yes, it'll have these many zeros, but I can't tell you exactly how it looks like. Okay. So yeah, so this is E1, E2, E3, and so on. So in general wells also, not only this, right? Now we are talking about a one-dimensional potential well. Not only this, the zero crossing theorem is very powerful, so powerful that we can consider a three-dimensional potential well, or even more than three-dimensional potential wells. More than three-dimensional potential wells, for example, come into picture. They're not physical, but imagine, you have rotational degrees of freedom and so on. If you have rotational constraints, you can think of higher dimensional potential wells. Okay. So anyway, not to confuse you, let's look at a three-dimensional potential well, which is our atom, right? So imagine an atom. So imagine a box like this, which is a three-dimensional potential well, right? So the very first eigenstate for this guy will have no zero crossing. That is your S orbital. Everybody, SPDF, everybody remember, I hope, right? And if you remember, we draw it like that, right? S orbital. The next orbital is P orbital. If you remember, P orbital always, either they're like that, like that, like that, and so on, right? I hope you remember this, right? So see, 1 zero crossing, right? Very nice. If you go to D orbitals, next is D orbitals, they'll have 2 zero crossings. If you go to F orbital, they'll have things like that. It's not entirely so simple as this, because this P orbital, D orbital, you need to consider other coordinates also, right? So so this is a little bit harder. I don't want to generalize, but I'm just giving you an idea that if you go look at the Eigen functions of Schrödinger's equation in a hydrogen nucleus, for example, which is the solution for an atom, there also you will discover similar kind of ideas. You'll have energy eigenstates, but they'll be now functions in three-dimensional space. And they will also have this very nice pattern of zero crossings. So if you see something that has more zero crossings, you know that it must be a higher eigenstate. And yeah, okay. So we'll if we get a time, we'll go into that. So it's very nice. But now I cannot answer that, right? So they have a zero crossing theorem. This is the idea. Okay. So these are not, I think I've covered everything now with respect to energy eigenstates and all that. This is your solution in a infinite dimensional potential well, right? The intuition must be very clear to you, right? The moment I put an electron in a confined state, its energy is always going to be less than the highest energy, right? So, for example, if you go to a finite potential well now, right? So let's say this height is fixed, it's u naught. Now, if I have a trapped state, its energy must always be less than this particular level, right? If I consider this as 0, that means all the trapped states should have their energy should be negative. Okay, it should, because see, if it has an energy that is larger, that means it's no longer trapped, right? Okay, so if I take this as the reference level for a finite potential well, all the trapped eigenstates must have negative energy with respect to this, and all the these kind of states, there will be states which have higher energy than that. They are definitely mathematically possible. These are called scattering states. This is also very important. This is what gives us now the idea of a tunneling and so on, right? So these are called scattering states, and these are delocalized. And these states which have energy lower than the barrier, these are trapped states or confined states or local, whatever you want to call them. They're called trapped states. And these are localized. Okay, now I'll give you an example, right? So let's take a semiconductor. We haven't covered a semiconductor yet, but I'll give you an example from semiconductor physics only, to give you an idea of these trapped states and so on. So let us say I have this semiconductor, piece of semiconductor, and there is a dopant, okay, which is a impurity, right? Donor or whatever, right? Maybe it's an impure atom is there. So there will be some electrons which will be traveling within your crystal. They'll be your scattering states. Okay. Sometimes, however, there will be trapped states also. They'll be completely trapped at this frequency. So that all these kinds of things are possible. Okay. Does everybody understand very briefly the idea, the difference between scattering states and trapped states? Right. So if I have an infinite potential well, the idea of scattering states doesn't come in. All states pretty much are trapped only, right? Well, not entirely. I could have I could have a situation like this. So maybe I'll have a situation like this, very deep well. This is our reference. Now imagine an electron that has now we solve the Schrodinger's equation and we derive eigenstates, right? I could derive eigenstates here. These are scattering eigenstates. Then I could have eigenstates that are below here, eigenenergies that are below the reference. These are trapped. These are localized. Why am I drawing a finite arrow? Because they cannot go beyond the well. These are your trapped eigenstates. These are your not scattering states. Why do I call them scattering states? The reason I call them scattering states is because once they hit this barrier, right, so part of it will go back, part of it will go forward. Okay, it is like this. Let me give you an example. Imagine a road. Okay, there's a road here, and road में बहुत बड़ा गड्ढा है. Okay, and imagine there is a ball that is coming here. Let us say the ball is coming in very slowly, doesn't have much velocity. Oh, गड्ढे में गिर गया basically. Okay, so you cannot escape, right? But imagine now having a ball that is going reasonably fast. So what could happen? The ball could actually go, right? It's like a car, bada car hai, gadda, you just jump a little bit, you go back, right? But also the ball could bounce back, it could maybe hit this portion of the wall and hit back, right? So that is why there are three possibilities depending on my energy. Either the electron gets trapped inside the well, or it gets scattered. It could get transmitted or it get reflected. Okay, so I hope things are clear now. When we jump from see, we only mathematically solved for infinite potential well, right? But from observing the pattern, mathematic pattern there, we are able to judge a lot of things. And first of all, about the trap states, we have the zero crossing idea, right? Now you may ask me, okay, that is great. We can write these trapped states in this way. This is the wave function, right? What is the wave function for the scattering states? You already know the answer to that. Those are free states, right? Those are simply, see, we already solved for the in free space, na? We already solved for the wave function in free space. Scattering states are simply plane waves. They're just that only.
Sir,
Yes.
Sir, this is in same diagram. This is a scattering state. Then it's a scatter after hitting the first boundary. Yeah, this is second. Here is like a, if we consider this is a first boundary and this is a second.
Right. So that's a good question. And what will happen is that it will actually scatter. There will be partial scattering from this wall and partial scattering this wall also. Okay. And there will be multiple reflections also. Okay, this is a very good question. And you are exactly right? So this is it's not that simple. See, there is two walls here. Dekho, plane wave aa gaya. Either portion of it will get transmitted, portion of it will get reflected. Portion from here also will again go like that. Multiple. Do you understand?
Yeah. Yes, sir.
So all these reflected waves will add each other coherently. All the transmitted waves will add each other, and you have to add all of this, and you have to add all the reflected waves to get the actual total reflection. Add all the transmitted beams to get the total transmission. That's a very good observation. You are absolutely right. It will actually scatter off of both of the boundaries. Okay. So yeah. Any question about this?
Sir?
Yes.
Sir, regarding the scattering states, why are they discrete?
Scattering states are not discrete.
Yeah.
Okay. Only the trap state have discrete energy. Okay. That's a very good point. Yeah. In fact, I guess the way that I have drawn here, it's confusing to you. No. They have a continuous energies.
Thank you.
This is a very good observation. Yes. Right. So because scattering states are simply plane waves. They're in free space, so they have continuum of energies. Very nice observation. Yes, and these have discrete states. Okay. Any other question about these scattering states and trap states? Remember, all we have done is we simply solved Schrodinger's equation in free space. Then we solved it in a very idealized infinite potential well. But just having mathematically solved these two is going to enable you to understand a lot of quantum phenomenon already. And let us keep going into some of those observations. For instance, if I have a semiconductor, very pure semiconductor, with a so let's do this, right? So I have a very pure semiconductor. How I do this? I take a very pure piece of semiconductor like this. Then on top of this, I'm going to deposit a second semiconductor, which is very pure. Very thin layer of second semiconductor I'll deposit. And lastly, I'll deposit my original semiconductor again on top of that once more. I hope everybody visualizes this, right? ऐसे मैंने ऊपर drop कर दिया इसको. So if I look at it from the side now, it's going to be black, yellow, black like this. 3 layers, black, orange, white, like this. This is my semiconductor. This is my device, right? So now imagine electrons, now imagine you have applied a potential like this. So electrons are going to be going like that, right? So now you have all kinds of very interesting things happening. Let us say I do this experiment. Okay? I'm going to basically have different voltages on the x-axis, and that is tantamount to how much energy the electron has pretty much. And on the y-axis, I'll have IV. So I have an IV curve, right? So imagine, can you imagine what the IV curve looks like? The IV curve of this particular device has a very interesting feature. It's going to do that, and it's going to have ripples in the IV curve. Okay, why are these ripples coming in? These ripples are coming in because of these multiple reflections and all these other phenomena, right? Yeah. So anybody who has done optics will not be surprised at this, because in optics we know this multiple reflection thing very easily. But when people in the 1980s, they typically when you did transistors, you measured the IV curves. How your IV curve used to be? The IV curves are always like this, right? Very smooth, nice kind of curves, right? Then when they started doing these experiments, they're very surprised, because on very small transistors, if you were to do IV curve, it will always show some very interesting dips, rings, and so on. It'll do all these kind of things. Why is that? This is again a signature of the wave nature of electrons. It's any discontinuity that is there in the crystal, the electron wave will reflect off of it, partially reflect, partially transmit. Then there's going to be interference between multiple things, right? We can also think about it this way. Imagine electron is coming here, a traveling state. Part of it might get lose its energy and become trapped, right? What will happen if that is the case? Then you won't see any current, right? Because whatever until the trap states are completely full, you will not see any current. So you'll be applying your voltage. After a certain amount of voltage only, you'll start to see any current. Okay, so we have a very nice threshold like behavior. So no current, and then boom, suddenly current will increase, right? We have a threshold like behavior. And the reason for that is, when you have traps, you have to first fill the traps. Only when the traps are entirely full, then only your electron can pass through that. So that is very nice. So if you have traps in your system, you will see some threshold like behavior. And second thing, if you have traps like this, because of these multiple reflections, you will see these in your currents, you will see these ups and downs in your currents. Okay. Again, these are signatures of the wave nature of electron. Great. So that completes our treatment of free space states. Secondly, it completes our treatment of infinite potential. Now let me show you the.
Sir, I have one.
Yes, please.
Sir, this ripple kind of the nature, sir, it can depends on the a thickness of the deposition.
Yeah, it depends on that exactly. So if your thickness is too much, then the electron current will lose its coherence. That means it's too large. Then you may not see these ripples. Okay.
Thickness is high, then ripple is less.
Yes, absolutely. So the more go to the idea of an infinite thickness, that means these reflections, there's no interference between them, right? Imagine a situation where you increase D too much, make it very large compared to the electron wavelength, then you will hardly notice any interference effect. So you will not see any ripples.
One more question, sir. Yes. We deposit like a two kind of the material. Okay. Then what happen on ripple? Like a more or less?
You will have more ripples. It doesn't matter. See, ripples come because of a discontinuity.
Okay.
Any kind of a discount. So if you ask me, sir, आपने एक material करके दे दे, बोल दिया कि ripple आ रहा है, ठीक है? Hold on. Is my screen off?
Yes, sir.
Yeah, sorry. Yeah, see, the fundamental thing is not that whether there is one layer or two layer. No, what is the fundamental thing that causes these ripples?
Like this is
Discontinuity. There has
discontinuity.
to be a discontinuity, right? So yeah, if I put another layer, what will happen? You made more. You have given more discontinuities.
Yes, sir.
So what should happen? You should see more ripples. That's it.
More. Yes, sir.
That's it. Yeah, absolutely. Okay, absolutely. That's correct. So all that this does is, yeah, anytime you have a discontinuity, that is where all the interesting things happen. That's where the reflections come in. That's where the tunneling processes may come in. Okay, we haven't gone to tunneling yet, so maybe I'll not talk about tunneling yet. But yes, even without tunneling, let's say there is no tunneling. See, tunneling only happens if the energy is less than the barrier, right? In our case, the energy of the electron is more than the barrier. It's only scattering. So it's not tunneling, it's simply scattering. So yeah, even then, it depends only on the presence of a discontinuity. If you add more materials, no problem. You'll basically you start introducing more and more interference effects. That's all. Okay. Any other question about this? I hope the physics is clear to you, right? How we went from a very simple solution to a more intuition, right? So I'm going to do this very quickly with atoms right now. Okay. So what will happen to atoms? So remember our potential well, right? In first case, okay, maybe I should first talk about a finite potential well, then we can go to an atom. So let us first go from an infinite potential well to finite and see what happens. We'll not do mathematically first, we'll just think about it. So how do we define a finite potential well? Let's take a square finite potential well only. And we'll again take 0 as our reference here. We'll say this height is U0, electron volts. Okay. Now there will be some wave function phi that solves this particular case, right? But what it is, we'll worry about it later. But it'll be some energy eigenstate, right? So it'll have some E1, some E2, E3, and so on. For it to be trapped and localized, by necessity, all these eigenstates must have energy less than U0. Right? Will we find one or not? That is another interesting question we'll come to later on. But if you do find an energy eigenstate, whatever eigenvalue you find for it must have a value less than U0. If not, it won't work. Great. And by zero crossing theorem, we know that the first eigenstate should have it should not have any zero crossing. So it should look something like this only, no? However, because the U0 is finite, for an infinite potential well, the wave function went to 0 completely at the walls. Okay, but that is no longer possible here. So now there is some finite probability for the electron to exist outside of the well, even if it has an energy less than the barrier. Okay, it may not have energy to completely escape. Okay, but it will still be, there is a small probability of you finding that electron outside the well. Okay, this is, why is this happening, right? Why is this happening? And this is the initial beginnings of your tunneling idea, right? This is more fundamental. This is the reason why tunneling kind of things happen. And let us examine this. In order to examine this, we have to take a mathematical excursion. We're going to go look at the Schrodinger's equation, and we're going to start thinking about a few things, right? So first things I want to think about is the wave function, continuity of the wave function, differentiability of the wave function. We're going to look at some of those aspects. And when we look at some of those aspects, we have to conclude that wave function has to exist outside. Okay, so it's it becomes a mathematical necessity. Why is it a physical necessity? That we will see once we understand the mathematical part. I'm sure you might get it once we do the mathematics. Hopefully it may strike to you also. But in any case, I'm going to go over it again, right? Great. So we can go back to our Schrödinger's equation. The time independent one. With a time invariant potential well. Okay. This is not varying with time. Of phi of x is equal to E of phi of x. We're going to do something with it, right? What are we going to do? What we're going to do is we are going to integrate this equation. You might be wondering, why the hell are we integrating? Doesn't matter, right? I want to integrate this particularly at this boundary region because we want to understand what happens there, right? So we're going to integrate around that region. Okay, so let's do that. I can integrate. No, it doesn't matter. I can definitely integrate. So let's integrate that. So I'm going to integrate at some position x minus zeta to x plus zeta. Okay. Maybe I'll do a plus zeta, a minus zeta to a plus zeta. Yeah, because this is x is a, right? Okay. And minus h bar squared by 2m squared by dx squared of phi of x plus a minus zeta to a plus zeta u of x phi of x d of x equal to e times, because e is a scalar, I can pull it out, a minus zeta a plus zeta phi of x d of x. And then I'm going to do something crazy because we are interested in exactly understanding what happens right at this boundary, isn't it? So I'm going to do something funny here. What I'm going to do is I'm going to take the limit of this particular process as zeta tends to 0. Why am I doing this? Because I'm really interested in finding out what happens to the wave function as I cross the boundary. Great. Fantastic, right? Now we have to do integrations, right? So always when you have to do integration, figure out which are the easiest terms, do those first. So we have 3 terms here. Term number 1, term number 2, term number 3. You have the easiest terms first, right? Let's do the easiest terms first. Last term appears to be quite easy, so let's do that first. So if I integrate any particular thing, f of x, phi of x, d of x, I'm going to get some other function, and if limit z tends to 0, this is very the area under the curve, right, of some function going from a minus zeta to a plus zeta. And as zeta goes to 0, what happens? This thing is kind of, so it should go to 0, right? It should go to 0. Except under one condition. What condition is that? When will this integral not go to 0? When will this limit not be 0? Anybody? I'm integrating a function from a minus zeta to a plus zeta, and I'm letting zeta go to 0. Okay. And clearly any normal function you can think about will go to 0 only. You can do x integration, x dx from 4 to 4. What is it? 0, right? But there is one function, one function which will not satisfy this. Anybody?
So the delta function.
Exactly, right? So yes, unless and until this third term is 0, unless and until my phi contains some kind of a delta. Now let's examine, is it possible for my wave function to have a delta? No. Why? Because if it was a delta, if it became a delta, then anybody?
The discontinuity issues will
Exactly, right? It will be discontinuous. So it's not possible, right? So we can conclude that this last term must certainly be 0, regardless of whatever happens, whatever function you have, whatever wave function, whatever potential you have, doesn't matter. I'll violate the condition of continuity. Because the probability of finding the electron at any point must not depend on whether I come from this side or that side, right? So it's not possible for me to have this case, right? So I integrate the wave function. So the third term is gone. Great. I want to replace all of this, bring that to 0. I know that this is always going to be the case. Great, right? So now let us look at the second term. Right? Once again, the same idea. Now the idea is that if phi of x cannot, but u of x can contain a delta function, right? So if it contains a delta function, then clearly this term will not be 0. Right. So we don't know that. We know that in general u of x can contain a delta function. We are allowing delta potentials. We're not allowing delta in a wave function. Because if there was a delta in the wave function, then it will be 0 pretty much everywhere else. Right. So so it's not possible. We know that it should have infinite energy. If it's a delta, if my wave function is a delta, that means it is some position eigenstate, right? That means it is at a fixed position. That's not possible. So physically we allowed that out, but potential we're not going to impose that condition. We're not going to say that potential also cannot contain any delta. In general, any potential we can construct in real life will never have a delta. Okay, simply impossible because it's not found in nature, right? It's unnatural. But mathematically, it'll say, oh, yes, we will allow it, right? If it indeed ux does not contain any delta, then the second term also must go to 0, right? So we'll say that the second term is 0. It's not, in general, it's not 0 if u has a delta at x equal to a. It has to have a delta at x equal to a only. At any other, right? Okay, that much is clear. Great. So we got the second term. Now let us see the first term. What happens to the first term? So I have minus h squared by 2m. I am integrating a minus zeta to a plus zeta. d by dx of phi x dx. So if I integrate the derivative of some function, so you can clearly see that this is going to be equal to square root by 2m d by dx of phi of x a minus zeta to a plus zeta. Plus second term. I'm going to leave this as second term. Okay, equal to 0. If the second term is 0, third term is 0, that means by necessity, the first term must be 0. And if right, so let us expand that. So that is h square by 2m into the derivative of phi x at a plus zeta minus the first derivative of the wave function at a minus zeta plus the second term must be 0. If my second term is 0, which means my u does not have a delta function at x equal to a, then automatically I know that the first term also must be 0. And hence I conclude that the derivative of the wave function is continuous unless and until, unless u of x is x minus a. Okay, fantastic. So this is where our idea comes in. So now I have this finite potential well. Now, initially I had an infinite potential well. Here we said phi of x is 0 outside the well, because it literally needs infinite energy, because otherwise that is the only possible state, right? The moment you say psi of x is located outside, that means I know that it should have infinite energy. So that's why we ruled it out. But here we cannot really rule it out. So when we try to solve the Schrodinger's equation, remember we have to say phi of x is we cannot say it is 0 for x less than a or less than 0. Cannot do that. Why? Because it's too restrictive, right? Nobody says that it's not possible. So unless until you have to check whether you have to allow
Sir, your voice is not audible. Hello?
Yes, sir.
Hello, when did I get cut off?
So I guess 10 minutes back.
10 minutes ago.
Yes, sir.
Yes, sir. Actually, we were able to reconnect it, but we weren't able to.
Okay, no problem, guys. Everybody here already, or somebody left already?
No, sir. Everybody's here, I think.
I'm so sorry, guys. let's it's okay. I don't think you missed anything. I'll repeat it, right? So what did I cover? Did I cover this part with the derivative has to be continuous? Hello?
No, sir.
No, sir.
Did I not start this only?
Sir, you started this, you were at this figure of potential and you were drawing that wave, and that's where the screen shows.
Sir, up to del function.
Okay, so okay, let's go over this once again. Okay, did I explain why the third term has to be 0? I think Prankush was there. I remember that.
Yes, sir. Yes, sir.
Yes, sir.
Okay, so the same logic holds for the second term also, right? Because it's just a multiplication of ux and phi of x. So when will the second term be 0? Unless and until phi of x does not have a delta function, unless and until u of x has a delta at a, this integral will be 0. Is that clear to everybody?
Yes, sir.
Okay, that's okay. So the second term is also 0, right? So yeah, this is what I was saying. Now we come back to the very first term. So first term can be written as minus h square by 2m a minus zeta to a plus zeta. Double derivative can be written as d by dx of phi of x d of x. Okay, and when you integrate this, it is simply d by dx of phi of x, right? If I do integral of d by dx of f of x dx is nothing but f of x, right? From the limits a to b. So if I use that idea, I can write the first term as minus h square by 2m d by dx of phi of x, derivative of phi of x at a plus zeta minus the derivative of wave function at a minus zeta. And if the u of x does not have any delta function, then both the second term and third term are 0. And so we have proved that unless and until my potential has a delta at x equal to a, the derivative of the wave function is continuous. Okay. Now we don't allow the wave function itself to have a delta function, right? We don't allow that to happen, but we allow why do we not allow that to happen? The reason is that if the wave function had a delta, remember integral of a delta is 1, right? So if the wave function had a delta, that means it is located exactly at that position with 0 uncertainty, right? And we don't want those kind of states. Those states are not correct because it will have infinite energy. So clearly wave function does not have any delta. Now we allow for the potential function u of x to have a delta function, right? So connection is okay, right? Everybody can hear me.
Yes, sir.
Okay, thanks, guys. Sorry, I just want to check again. Yeah, so we allow for potential functions to have deltas. That's okay. In real life, however, there is no infinite potential. My potential function cannot be a delta in real life. Why? Because that would need infinite amount of charge to create that delta potential. But if a potential well is reasonably steep, then we can approximate it using a delta function. So we allow that, right? So if there is a delta function, only then do we have a derivative of the wave function is not continuous. So in every situation and in every consideration in real life, the wave function must be continuous and differentiable. We use this condition, we use this derivation in solving for the wave function in the finite potential well. Okay, let me, before going into the mathematics, let me tell you something here, right? So if we say that the wave function must be exactly like what we got in the infinite case, then it turns out that that is not going to be able to solve Schrödinger's equation. So it is a mathematical necessity that the wave function must essentially be non-zero outside even the ground state. Any Eigen solution will be non-zero outside the well region also in a finite potential well. Okay, this is a mathematical necessity because any solution you can try which is zero outside, it will not solve your equation. It will simply not solve your Schrödinger's equation. Physically, what this means is that your wave function, it doesn't actually leak out. Okay, it doesn't mean that it escapes, because you see the probability of finding the electron is actually decreasing as we go away from the wall. Okay, I hope this is. Let me explain this a little bit more carefully here, right? So we consider a potential well. Okay, and it's a one-dimensional potential well. So imagine a strip like this, where I have cut out a well. This is my well. Okay, and physically, right? So physically, the electron. What am I saying about the electron? What I'm saying is there is a chance of detecting the electron in this portion of the strip, this portion of the strip also. And this should actually really surprise you, right? Because in a classical situation, if you are trapped in the well, then there is absolutely no possibility for me finding you outside that well because you are trapped, right? But in quantum, this is the very funny part, is that I have a small probability of detecting the particle outside as well. However, there is no flow. Okay, there is no flow, meaning that the particle is not actually flowing. Okay, so I cannot detect, it's not moving, right? What do I mean by it's not moving? See, let me draw a road, right? So we draw this road here. There's a small gadda kind of thing, right? If I was actually free, then my probability of finding here as well as here should be similar, right? Because I'm literally moving along the highway. So yeah, and here also, right? So if I escape out here, so yeah, probability of finding here and here should be similar because I'm just moving along that highway. But the probability, what it does is it will actually decrease the farther you go away from the hole. Okay, this means that there is no flow, that it is indeed trapped. Okay, it is it's not flowing out, so it is indeed trapped, but there is still a probability of finding it outside, probability of detecting it outside, right? So it's very bizarre. Physically, I can never give you an example of anything like this. So if you ask me, if you insist to me, bhai kyun ho raha hai iska example de do, I cannot, right? But people have done many experiments on trapped states, and indeed they find this. Indeed they find that the electron is indeed, you're able to detect it outside. Okay, but the farther you go away from it, the less you'll be able to detect. Yes, right? So where is the equivalence for that in real life? There isn't any. I'm sorry, because there isn't any at all. If I cannot say that, if you're trapped in a room, occasionally I'll see you outside that room. It doesn't happen, right? If you're trapped in a room, you are trapped in a room. I'm never going to be able to see you outside that room. But this is what happens for the electron. And this has very interesting implications. One of them is that, your atom, right? Atom is like a potential well. It's a finite potential well. Atom is not an infinite. Atom is a finite potential well. So this is the reason why you have chemical reactions. All these kind of things usually happen for this reason, and chemical bonding. All of those things happen for this reason. If it was, if this was not possible, then two atoms would never be able to form a chemical bond. Because what is a chemical bond? A chemical bond is basically saying that one electron can belongs to like both the atoms in a way, right? So without this leakage, that is simply not possible. Okay. Yeah, I'll pause. Anybody has any question now, please ask. Okay, because I'm sure this maybe you find it a little bit difficult to digest, and I'll try to make it slightly easier, but I cannot give you a physical example because it doesn't exist. Only the electron does this, or not just the electron, any quantum particle will do this, but not any object that we see in our daily life. Anybody? Okay, I guess I'm doing a decent job of explaining this, right? So it's fine. Let's see where we are on time. I think we finished on time. So I'll catch this up next time. Where in next class, we will continue to deal with how to solve the Schrodinger's equation of finite potential well. And we'll understand, what the eigenstates will be, what the wave function looks like, all those things. After that, we'll go into the tunneling problem as well. Hopefully, I'll be able to do all this in the next class. And if there is no other question, I think we can wrap.
Thank you, sir.
Thank you. Anybody? No, nothing, right? We can wrap, right? Okay. Thank you.